Yeah, so I'm playing both myself and Doug in this talk, and he's sorry that he can't be here, but on Thursday he's flying to Australia, and that will be the 7th continent that he's visited in his life. In last December he went on a cruise from the very southern tip of Argentina down to Antarctica and actually slept on the ice in Antarctica. That must have been memorable. For Antarctica. I'm not going to go there. And you know, he said, so now I've been in 7 continents, so I'm incontinent. And so that's classic Doug. Here we are. That frog in between us is holding up a glass of champagne. This is a shot of us after one of our seminars when we went to wine tasting for a day. This is Steinberg winery, where they taught us how to make sparkling wines, which involves a process called riddling, where you turn the bottles 1/3 of a turn every few days, and that's supposed to make things much better. I'd like to do an experiment on that. I'm supposed to talk about Stu and his impact on design experiments and quality methods. And so my vote for his biggest contribution is a contribution that he made with George Box and Bill Hunter, they're appearing here. And I think this is the picture that was your last picture, right?
Yes.
This happened at a Gordon Research Conference. And Gordon Research Conferences on Thursday night always had a talent show. And the talent show, people did skits, made fun of talks that were done earlier in the week. Dick did the weather report, which in Swedish. That was really amazing.
Unless you're Swedish.
Especially if you're Swedish. And you know, for me, as a young statistician right out of graduate school, I went to graduate school at Florida State, and then my first real job was in Rockwell International, working with chemists and physicists and engineers designing experiments. And I didn't know anything about designing experiments, but in order to get started with that, I actually had to get a Q clearance, which is a secret clearance from the Department of Energy. And my Q clearance took a long time to come, which is a good thing, because until I could actually get inside the gate, I couldn't actually do any statistics. So in the meantime, I read this book, cover to cover, and did all the problems. And by the time I finished that, 6 months outside the gates, I was a barbarian ready to storm the gates. And this book made a huge difference in my understanding of how you go about doing a design experiment. And my original training was in chemistry and physics. I'm used to thinking of the world as being nonlinear. The notion of two-level factorial or fractional factorial designs and a linear model, I thought was probably too simplistic. But my first because, when you do an experiment yourself, when you actually design and analyze and participate in an experiment, and you see those kinds of results, it's memorable. Anyway, this made a huge difference. So, and a big part of that book is the several chapters, starting with two-level full factorial designs, fractional factorial designs, and learning how to, and then blocking those designs. That are all, and this material is explained in this great two-part paper in Technometrics in 1961. Oh, by the way, so in this slide I'm playing Doug. See, when I have produced a slide, it has jump, and when Doug has produced a slide, it has everyone stay. So this is Doug's slide. So he talks about George and Stu talk about generators, defining relationships for columns in the design, and the concept of resolution, fold over, and so forth. I wrote a blog about this paper earlier this year in honor of the International Year of Statistics, and I wrote several blogs primarily about George Box, but of course Stu's going to be sneaking in here. Here's a mention of Stu. In the last paragraph, which I don't think you can read, so I'll read it for you. This seminal paper is 40 pages long, and one thing I found notable about it was that the mathematical content did not go past arithmetic and a little algebra. Despite this, there are many fundamental results in this paper, but all are stated in natural language without formal proofs. That was refreshing. And that's also amazing. So, anybody who could understand algebra could understand this 1961 paper. It was amazing. So what they did, they started out with a 4-factor full factorial experiment, 2 levels, and the construction of those is fairly simple. Then they showed how to fractionate that by starting with a full factorial and doing a half fraction, started with a full factorial in 3 factors, and then create the 4th column by confounding it deliberately with the 3-way interaction of the 3. And so then you can reconstitute the full factorial by just folding it over. So that gives them the fold over idea. Then they have resolution coming out. They also talk about saturated designs, so designs where n equals p, where p is the number of parameters that you want to estimate. And they throw a bone to Plackett and Berman, who had these 11-factor designs in 12 runs, or 23 factors in 24 runs, and so on. Still more stuff. They talk about how to block these designs with blocks that have some power of 2 runs, and that enables you to partition the variation that you can't control, but by grouping runs that are homogeneous. And then they talk a little bit about projection as well. So this idea of projectivity, and that designs that are originally thought of in a k-dimensional space where k is the number of factors, if it turns out that some subset of factors aren't important, then you project down on a much smaller space, and then the design can even become a full factorial design in that smaller projection. Actually, speaking of that, there was a conference in the Netherlands that has been mentioned before today, and it turns out that George Box came to the United States with this prop, there was a long, thick piece of wire or a rod connected to several rods that created a cube. And so this prop, so you have a cube with a handle that and then you can show how the cube projects down onto a square in all three dimensions. So so George gave that cube to Stu, and Stu gave the cube to me. I couldn't believe it. It's wonderful. I thought about bringing it, but it just doesn't really fit well into the luggage. And the next thing I wanted to talk about is his work in RSM. Of course, there was the big paper in '51 with Wilson, but this paper here in '57 actually appeared in the Annals of Mathematical Statistics and introduced the idea of rotatability, in which a design is rotatable if the variance function is constant on spheres that go out away from the center of the design. So they introduced this prediction variance formula in that paper. They also had formulas for the aliasing of a set of coefficients by a set of coefficients that are not in the model. They also even had a formula for the aliasing of the estimate of variance by terms that are not in the model. Those are formulas that I've seen in recent papers talking about multi-objective optimization in design. So a lot of follow-on papers had to do with taking this idea of the variance function and thinking about ways of looking at the variance function of a design and learning and comparing designs by comparing their variance functions. So there's the paper by Ray Myers and Gio Benson, Curry Kim, Christine Anderson Cook, and her graduate student, and so on. One of the things that I've really liked about a plot that I really liked came out of the thinking of Christine Anderson Cook, and that is the fraction of the design space plot. So the y-axis of this plot is the prediction variance, and the x-axis is the fraction of the design space that's being that you're looking at. And what it is a quantile plot of the prediction variance function. If you were taking a uniform sample over the space, and these are the quantiles that are being plotted here. So, for instance, if you look at this vertical line, that's the median. So half of the design space has prediction variances that are less than or equal to, roughly 0.22. So this is a fraction of the design space plot for a rotatable simple composite design. Very pretty idea. The way you create such a plot is you create a random sample, a very large random sample of points, and then you order them, and you plot the order statistics. That's the blue line. So it's very easy, very fast. Here is a design that's a rotatable design. It's a pentagon, a regular pentagon with a center point, and this is a contour plot of the variance function for that design. And one thing that I wanted to point out is that the variance in the middle here is a little higher than the variance in that circle there, and then so the variance goes up towards the center, goes down, and then comes back up again. So one of the things that Stu and George Box talked about was you can put more points in the center and drive that variance in the center down so that the variance rises smoothly up from the center, and that some people call that uniform precision. This, if you were only going to have 6 points, and this would be a saturated design for a full quadratic model, and this is the optimal design for this problem. If you're only going to have 6 points, and then here's a hexagon, regular hexagon with 2 center points, and again the variance function for that same idea. But again, rotatable designs, interesting ones. Not that other rotatable designs aren't interesting. Again, I'm going to put my Doug hat on and talk about this piece of Doug's talk. This is a piece of Doug's talk from the conference in Heemskerk in Netherlands in March, which was an entire conference that was done in honor of Stu Hunter. It was a great conference. And so Doug talked about this paper that Chris Knoxheim and I wrote. And then, of course, how could I resist not putting this part of it into this talk? So, of course, Roger just talked about how design should be sequential and how you shouldn't think in terms of trying to do everything in one shot. But my thinking is that and this is due to the fact that a lot of my own experimentation has been done with situations where each experimental unit was really, really expensive. So you want to get as much out of every run as possible. So if you're lucky, you might be able to do optimization and screening, or screening and then optimization all at once. And these designs have potential for that. This is the pattern of the design. The design is created out of fold-over pairs. It's spherically symmetric because every point is, if there are m factors, it's m minus the square root of m minus 1 from the origin. Every run has a 0 in some column, and every factor has high values, low values, and middle values. So these so-called definitive screen designs, unlike resolution 3 designs, they have main effects and two-factor interactions independent of each other. Unlike resolution 4 designs, though, even though these designs are foldovers, the two-factor interactions are not confounded with each other. So it's possible to uniquely identify a two-factor interaction as being the causal effect here. And unlike any of the two-level designs, the fact that there are 3 levels in each factor enables you to fit quadratic effects that are strong in any one of the factors. So unlike those designs, the 2-level designs with center points, where you can get an omnibus measure of curvature, with these designs, you not only get the fact that there's curvature, but you can assign the curvature to a factor. So, and then these designs also have very nice projectivity in the sense that for any 3 factors, as long as you have more than 6 factors in your design, for any 3-factor projection, you can fit a full quadratic model in those 3 factors. So it turns out that if there are only 3 active factors, no matter which 3 they are, you can fit a full quadratic model. So they are sort of like a greedy responsiveness designs. So Chris and I found these designs by using some optimization technique, but it turned out a year later, Dennis Lin and some co-authors pointed out that there was a combinatorial approach that you can use to create these designs instantaneously. And so from that point on, people have been doing that and not using the optimization approach. I want to talk a little bit about the Taguchi controversy. In the mid-'80s, Stu and a number of other people from American statisticians were in reaction to a number of ideas that Taguchi had. I think this was a good thing for United States statisticians because it started focusing our thinking on variability being just as important as the centering of a process, and thinking in terms of how one might make products robust to transmitted variation from an inability to control certain factors. Stu and George Fox were both very active in that part of what was going on in the 80s. And then here are a number of other articles that I thought were notable, especially this number 2 here, Hunter and Naylor, Experimental Designs for Computer Simulation Experiments. Look at the date. What was it, 1970? Amazing, because that's a really hot area lately, but you know, 1970 is prescient. And then, of course, Roger talked a lot about the exponentially weighted moving average. Actually, Stu doesn't remember the first time he met me. He thinks that it happened much later, but he actually gave me a course one time on the exponentially weighted moving average, which I thought was really great. And then this last one, the National System of Scientific Measurement in science. So that's